At dawn, the Tonga Trench lies invisible beneath a Pacific surface polished by distant winds. Far below, a curving wound marks where one moving plate descends beneath another. Its violence is not a permanent explosion, but strain accumulating across immense slabs of rock. The trench, therefore, records motion through steep relief, earthquakes, deformation, and altered seafloor sediments. From a ship, you see only water, while an active plate boundary passes underneath. The mystery begins with that contrast between calm light above and restless geology below. Why does this particular scar plunge so deeply beside an arc of volcanic islands? What happens as old Pacific seafloor bends downward and enters the planet's interior? Direct measurements reveal the shape, yet the forces producing each fracture remain partly hidden. Earthquakes illuminate portions of the descending plate like brief lamps inside an enormous dark machine. Bathymetric maps show a narrow depression stretching northward through a complicated zone of plate interaction. The opening image is deceptive because the trench is neither isolated nor mechanically uniform. Its slopes carry collapsed material, faulted crust, and sediments disturbed by recurring tectonic movement. Every ridge and basin reflects a contest between plate bending, convergence, erosion, and local structure. The investigation follows that contest from the seafloor downward, separating measured change from geological inference. The Pacific Plate moves generally westward here and sinks beneath the northeastern edge of the Australian Plate. This process, called subduction, recycles oceanic lithosphere into the mantle over millions of years. The descending plate is unusually old and cold, allowing it to remain dense as it bends. That density helps drive descent, although mantle flow and regional plate forces also contribute. The boundary curves sharply near Tonga, producing changes in direction, speed, and stress along strike. Behind the volcanic arc, the Lau Basin opens as the overriding plate stretches apart. This back arc spreading distinguishes Tonga from simpler textbook diagrams of one plate sliding beneath another. Convergence across the region ranks among the fastest measured at modern subduction zones. However, movement distributes across several faults, so no single number describes the entire system. Multibeam sonar traces the trench floor and walls by timing sound reflected from the seabed. Seismometers locate earthquakes, whose waves pass through rock with different temperatures and compositions. Satellite geodesy measures surface motion on islands, connecting short human observations with plate-scale deformation. Rock samples and sediment cores provide physical evidence of crustal age, chemistry, and repeated disturbance. Together, these four methods reveal structure without exposing every process directly. The trench axis reaches Hadal depths, where pressure exceeds 1,000 times that at sea level. Cold water fills this realm, while sunlight has vanished several kilometers above. Fine particles descend slowly, but steep slopes can funnel sudden avalanches toward the axis. Those flows redistribute organic matter and erase portions of older sedimentary records. Trench is therefore both a geological boundary and a collector shaped by gravity. Volcanoes west of the axis arise when fluids released from the slab alter the mantle above. Lowered melting temperatures help generate magma, although individual eruptions follow complex storage and ascent pathways. Volcanic arc and trench are surface expressions of one connected subduction system. Yet their visible spacing varies because slab angle and overriding structure change along the boundary. Evidence sharpens where earthquakes descend beneath Tonga to remarkable depths within the cold slab. Shallow events often involve brittle faulting near the plate interface or bending outer rise. Deeper events occur under pressures where ordinary shallow fracture models become insufficient. Mainstream interpretation invokes transformations, dehydration, and localized instability within the sinking plate. No single mechanism explains every deep earthquake, and direct observation at their sources is impossible. Earthquake locations outline a steeply dipping zone, supporting the presence of coherent descending lithosphere. Seismic wave speeds also suggest a cold slab penetrating far beneath the island arc. These signals are indirect images derived from travel times, not photographs of hidden rock. Resolution weakens with depth and uneven instrument coverage, leaving boundaries blurred rather than exact. When you picture the slab, imagine a constrained reconstruction built from many crossing wave paths. Large earthquakes test how stress moves through this reconstruction and across neighboring fault segments. Some rupture the plate interface, while others break within the bending or descending oceanic plate. Their depth, fault motion, and aftershock patterns help distinguish these settings. Tsunami potential depends strongly on shallow seafloor displacement, not simply earthquake magnitude alone. Deep trench slopes also permit submarine landslides, although identifying ancient triggers can be difficult. Sediment layers may record rapid deposits consistent with energetic flows after major disturbances. Such deposits require careful dating and comparison before any event receives a specific cause. The trench's extreme depth partly reflects strong downward plate bending and limited sediment accumulation. But local relief can change after faulting, collapse, or burial by transported material. Repeated mapping can detect major differences, though deep ocean surveys remain sparse in time. Apparent features from low-resolution sonar may disappear when examined with closer overlapping coverage. This is why unexplained shapes are treated as mapping problems before becoming geological anomalies. The most violent part of the scar is not necessarily its deepest visible point. Stored elastic strain may concentrate on shallower locked sections hidden beneath water and sediment. Geodetic measurements on nearby islands estimate coupling, but offshore behavior requires models and assumptions. Those models improve when seafloor instruments measure motion closer to the boundary. Until coverage expands, the distribution of locking remains an interpretation with meaningful uncertainty. Life occupies this active landscape despite darkness, pressure, cold, and recurring physical disturbance. Hadal amphipods scavenge sinking material using chemical and mechanical cues where vision offers little advantage. When food reaches the floor, they converge, feed rapidly, and redistribute carbon through movement and waste. Microbial communities process organic matter within sediments, linking surface productivity to trench chemistry. Their activity consumes compounds, changes pore water, and influences what carbon remains buried. Sea cucumbers move across soft sediment, ingest particles, digest useful material, and leave reworked trails. This feeding sequence aerates shallow layers and rearranges microorganisms across the trench floor. Species distributions change with depth because pressure, food supply, slope, and isolation filter survival. Researchers document these patterns carefully, without assuming every captured animal is endemic. The trench may concentrate organic debris, creating patches of abundance within an otherwise food-limited ocean. Disturbance can destroy those patches, then expose fresh surfaces for microbial colonization. Tectonics, therefore, shapes habitat through topography, sediment movement, fluid pathways, and episodic burial. If you descended there, pressure would require a vehicle engineered around a nearly flawless protective sphere. Lights would reveal only a narrow window, making each observation powerful but spatially limited. Landers sample longer periods, yet bait can alter nearby animal behavior and abundance. Unbaited cameras reduce that influence, but may record fewer encounters in the darkness. Every biological claim must account for this trade-off between seeing life and changing its actions. The human stakes rise along inhabited islands, facing earthquakes, eruptions, and tsunami-generating deformation. Hazard planning depends on recognizing that Tonga's boundary contains multiple sources with different warning times. Rapid earthquake analysis can estimate rupture, while ocean gauges confirm whether a tsunami is propagating. Neither system predicts every local wave perfectly because coastal shape transforms incoming energy. Clear communication turns uncertain scientific estimates into practical evacuation decisions. Future evidence must connect deep structure with motion measured directly across the offshore plate boundary. Denser seafloor geodesy could reveal where strain accumulates between earthquakes along separate trench segments. Longer seismic records could distinguish persistent patterns from temporary clusters in the descending slab. Repeat bathymetry could identify fresh ruptures, landslides, and sediment movement after well-recorded events. Carefully dated cores could test whether major deposits recur together across distant parts of the trench. Biological surveys across matched depths could separate pressure effects from differences in food delivery. The central uncertainty concerns how a curved, rapidly moving system partitions strain through time. Scientists can measure present motion, reconstruct past events, and simulate plausible future ruptures. They cannot specify the date, size, and path of the next great earthquake. That limit does not weaken the evidence that enormous forces continuously reshape this boundary. As evening closes over Tonga, the surface again conceals the trench beneath ordinary waves. Below, the Pacific plate continues bending, habitats shift, and stresses migrate through fractured rock. The scar is violent because motion persists, yet its next expression remains scientifically unresolved.